Good morning, my name is Clive Davis from Yokogawa. Today I will be talking about power measurement. The reason for that is we have a big range of product which can all measure power, but they all have different ways and different reasons for measuring power. And today I'll be trying to help you to find your way through this big subject matter. Good morning everybody. So as it says, I'm Clive Davis. I'm the marketing manager for Yokogawa in Europe and Africa for test and measurement products. My conversation today is all about power measurement. You're probably aware that there are a number of products available on the market to measure power, and so I want to help you to identify what the issues are and how you would actually make your choice. See if this one works. Okay. So basically fundamental questions. So first of all, I'm going to pose some questions at you and hopefully I'll answer them as I go along. First of all, ask yourself the question, actually, I'm talking about power, but what does that actually mean? Is the power itself I'm measuring repetitive? Is it stable? Do I also need to measure sub-cycle power or cycle-by-cycle power as it varies? What's the actual wave shape of the signals that's driving this power? Is it a pulse width modulated signal, for instance? So that, of course, does not look like a sine wave. It looks like a very complex square wave. Is my signals noisy? What about the wiring? What sort of, is it single phase? Is it three phase or a combination? All right, okay. First and foremost, you have to ask yourself the question, what accuracy am I looking for? That's driven by many factors. It's also driven by what stage you are at in your development process or design process, where some stages you can actually be more relaxed about the accuracy you're actually looking for or actually need. But when you get down to the validation or the tests against the standard, of course, then you have a very specific calibration or accuracy requirement. Am I looking to measure small changes in efficiency? It automatically means that you have to measure with very high accuracy. It is possible, if you're measuring with too low an accuracy, to get efficiencies of better than 100%. So this is, of course, potentially a big problem. The other issue is, how can I have confidence in the accuracies that I'm being presented with, the specifications I have on paper? And of course, is there a holy grail? Is there a perfect instrument which will actually suit all my power measurement needs? And what about cost effectiveness? So I'm going to try to address these questions. Until recently, we were using this picture. I mentioned to you about the fact that we can use different products at different stages in the process of your development cycle. So an oscilloscope, we've already seen an oscilloscope can be used to measure power. We have ones to do that. Our traditional oscilloscopes are 8-bit instruments. You've already heard about 12-bit. We also have another product called a scope recorder. It's more like a data acquisition system which looks like an oscilloscope. This particular product is available in 12 and 16-bit variants. It's actually a flexible product with pluggable modules. You won't be surprised to know that also is able to measure power or to monitor power amongst all its other features. And then we have what you can consider to be a traditional power meter. Now, power meter and power analyzer tend to be a bit the same these days, depending on the functionality. But first and foremost, they're a power meter. They basically show numbers on a display. So that's where essentially they're different to a visual type product like an oscilloscope, for instance. So a power meter is designed numbers, and that actually causes some issues about how you actually explain how it works or what benefits it has. So there are two basically types of product of the overall power measurement category. We have what you can describe as traditional types of averaging power meter. These are the types of devices which traditionally have numbers. They display numbers. Then we have the ones which rely on what you might describe as visual technology, digital storage technology. And we actually have three styles of product which meets these. We have the more traditional scope-based 8-bit type products. We also have our scope recorder type products, which offers high resolution. And more recently, we've introduced a product which endeavours to bring together the advantages of all these. Doesn't replace any of them, but it's another way, another type of product available to you depending on what you need to do with it. And I will now address those issues. So what's the basic differences between a power meter and an oscilloscope or digitized based product? Well, it's all to do with the fact that in a digital storage, an oscilloscope, as we know, basically acquires data and then it analyzes. If you're familiar with digital oscilloscopes, all digital oscilloscopes have dead times. They have times at which they're not looking at the input waveform. So they're ideal for looking at single-shot events. And of course, the holy grail for an oscilloscope is to minimize the dead time so you don't miss anything. So essentially, that's the drawback for using an oscilloscope type product, a waveform analysis type product for measuring power, because there are bits you miss. So if you are looking to integrate power and to look at your watt hours, you won't be measuring all the watt hours because there are dead times associated with it. So that's where a streaming type, a power meter type, wins, because it doesn't store the data. It's a continuous process, and basically it's acting fast enough that you have no gaps. So that's one key difference between a power meter and a visual or oscilloscope type product, is you don't have any gaps in analysis. It's actually doing its calculations as it goes. Just quickly look at the definition of power in its sort of basic sense. So basically we have an integration going on. We've got power, tiny differences of power, which in this case are sampled at whatever rate your instrument is sampling at. Generally speaking, of course, these days we're sampling voltage and current in some way, simultaneously, multiplying them together in real time. And then basically, in order to do power average, because this is a fundamental definition of power, we are then integrating it over a whole number of periods. And you can see that we can also then work out, if we continuously measure that and divide by t, we have the same result. This alone can cause problems, because what is the period and how do I measure the period? Because my period may be changing, I may have noise present on that, and it may be very difficult to do a real-time measurement of that period. There are various ways and other techniques within our power meters that we actually use where we don't have to measure the period. That will depend on the actual sample rate or the frequency of our fundamental of our signal, in actual fact. But essentially, most instruments, whether it's a power meter or an oscilloscope type product, we have to measure that period. Another issue, of course, is what happens if there is no period. In this case, we have a startup. Somebody may be looking for startups. You know, we basically have a big business into hybrid cars where you're looking at what happens when the load comes on, for instance, or other conditions where things are changing, where you have devices where you're not looking at constant power, you're looking at a process which has changing power levels. Let's say one example may be a printer, for instance, which has many processes within one product. So it is, of course, relevant to measure the continuous power, but from a development point of view, the engineer may also want to be looking at what happens when this particular part of the process kicks in. What effect does that have on the power? And so a traditional power meter won't allow you to do that, because it's essentially a transient based. And you can see, of course, as we've got an example here of a motor. As the motor kicks in, you have a changing cycle. So it'd be no use measuring the average power over a longer period. It's not going to give you any sensible result. So a few more questions I'll throw at you, or a few more ideas to think about. What accuracy do you need to measure? And basically that's also related to do what is the level and voltage and current, and how are you getting the voltage and current into the instrument, and what is the accuracy associated with that mechanism as well. We also have to consider what happens when we've got floating voltages. Standard oscilloscopes are single-ended, of course. They are ground referenced, except for instruments like our scope recorder, which have isolated inputs. And because you've got floating voltages, particularly on three-phase supplies, you have common mode issues, where common mode voltages will affect the accuracy you're measuring. So that's also something potentially you have to think about. What's the power factor? Because power factor actually has a big impact on the accuracy of the measurement at the end of the day. How distorted are your waveforms? We've got Crest Factor considerations. I'll talk about that a little more in due course. So what sort of effects on the overall measurement accuracy do I also get from Crest Factor? What bandwidth is necessary? Do I need traceability on my accuracy? Do I have customers who need to see that accuracy? What about the stability of the measuring instrument? We basically talking now about precision, and precision in many ways is not only to do with what the resolution of my measurement is, but how repeatable is it? Am I able to take a measurement one day and it's going to give me a similar reading the following day or the next year or in 2 years' time? I've already talked about the power level. Is it continuous or does it fluctuate, or is it intermittent? Just talk a little bit about Crest Factor, because it is relevant in the types of instruments you're using to measure. I'll explain why. So Crest Factor is the peak value of my input, and if you consider this, it's probably a possible current wave shape of an instrument, divided by the RMS value. So you can see that modern devices, instruments that go into standby power, for instance, where we're talking about 1 watt or even half a watt, they have very high Crest factors and quite low power factors as well. So it actually puts presents a big problem to the instrument you're measuring power for, because your ranging may be dictated by your RMS value, but your dynamic range must cover the peak value. On a standard sine wave, non-distorted, my Crest factor is 1.414. Well, it's not quite, it's actually √2, but 1.414, almost exactly. And basically it means that when I have very high Crest factors, my measuring instrument has to be able to handle those high Crest factors. So basically, when you've got an oscilloscope type product, which actually of course is fundamentally defined by peak measurement ranges, if you've got high Crest factors, your actually measuring portion, irrespective of whether you have high resolution or not, can be quite small. So that's where you definitely need as high resolution as you can get. So in practice, you can get Crest factors of 180 or even up to 300 in actual fact. So what I'm going to do is give you a few ideas. I'm going to give you a few pros and cons of the different types of instruments for measuring power. And I should say that when I talk about power, it means different things to different people. Because if you say power to an RF person, they'll be thinking of microwave power. We basically are talking about low frequency power, but the problem, and mainly to do with the supply frequencies as the fundamentals, 50, 60 hertz, for instance. But of course, modern devices and modern technologies and LED lighting or other high frequency usage means that there are elements of higher frequencies, and that's why you've got power meters which are specified at 1 meg, for instance, or even 2 megs. There are issues with that to do with how you prove or how you can show that your instrument is actually accurate at those instruments, because actually there is no international standards which actually offer you a guarantee of calibration at 1 megahertz. Essentially 100 kilohertz is the maximum you can get. So pros and cons, the oscilloscope. First of all, the one thing the pro is that most people have one. And the other thing is, by human nature, we are visual people. So intuitively, it's actually quite convenient to think of the fact that if you see a waveform on the display, and you can bring up a pair of cursors, which you think will be the cycle by cycle, you can get a measurement of power. And you can do that with any oscilloscope in actual fact. So it's an intuitive question mark product. There's probably one on your bench already. Lowish cost can vary because it depends on the quality of the oscilloscope, of course. If you've got one on your bench already, there's no fundamental cost, but if you can add, or there are available power analysis functions available on the instrument, it obviously means that potentially you can do it very quickly. You know, as I said, you can use a standard oscilloscope, bring in 2 channels, multiply them together, use the cursors up, and get a measurement of power. Even if you don't need to do all the other measurements associated with it, which normally you would have available for dedicated power measurement functions, for instance. And it's a flexible instrument. By nature, an oscilloscope is a general purpose instrument. So what sort of cons are there? Well, the problem with an oscilloscope is you'll find that accuracy on oscilloscope is only defined for DC. So this is where you get the thorny subject of what happens at high frequencies. How do you test the performance or measure the performance of your oscilloscope at frequencies other than DC? There are people that, or there are ways of doing this with talking about effective numbers of bits, but it still doesn't give you an overall accuracy measurement at high frequencies. There are additional errors due to the probes or transducers. You'll see that I have an example running here on a single ended oscilloscope which uses a differential probe and a current probe. Of course, these also have their inherent errors associated with that measuring system. And you've got the errors, potential errors, to do with the phase shifts between these 2 probes. They're not identical, so irrespective of what the internal phase accuracy of your oscilloscope is, which you would also have to measure in, you'd have to add in the phase errors on the oscilloscope. And of course, we also provide features to try to minimize that using automatic phase cancellation, but it's not perfect. They're never perfect. So what is the actual accuracy of your power measurement? Very difficult to calculate because you don't have all the information you need to do that. So reasons to use a power meter or analyzer, because essentially we use them a bit interchangeably, but really it's only an analyzer if it has more sophisticated measurement capability rather than just the numbers. So, and you can see we have a range of these things, some of which show some waveform and some that don't. So what are the pros? Well, overall, when you need to know what the accuracy is, you would potentially use a power analyzer. And I say overall high accuracy because there is a variation. As you might expect, it does have an impact on pricing and size of product, as it says here. We have direct input of the current and isolated voltage. So with this sort of product, generally you have shunts built into the product, and they have to be controlled very carefully in order to minimize the self-heating effects. And that, of course, is potentially what limits the maximum current that can go into the instrument. Because if you put in a lot of current into the shunt, they will heat up, and of course that will cause further errors in your accuracy. The other issue to do with this is common mode errors. You'll see that on an oscilloscope, for instance, or an oscilloscope type product, your common mode rejection ratio is normally specified in minus so many dBs. For a power meter, that's not sufficient because you never know what that actually means in practice. So you'll find on the specification for a power meter, for instance, you'll see what actually the effect on the measurement error, or yes, on the measurement error of common mode effects will be, and you'll see within our specifications that is stated. On some models, you can do cycle-by-cycle measurement. On our highest end power meter, our most accurate one, you can actually do cycle-by-cycle measurements, and of course that is continuous, again without any gaps, which you have with an oscilloscope type product. And of course, also, there are different capabilities needed. So if you're measuring in an inverter-driven system, and you also want to build in not only the electrical efficiency of an inverter, but also want to do the mechanical efficiency of the whole system, we also have to input in the input from torque sensor, for instance, which measures both torque and speed of the motor. In this way, you can also get the power meter to calculate both electrical and mechanical efficiencies, for instance. And so this generally is available on some or all types of power measuring product. And because there's a range, you can have different models. So, of course, one need for this is, let's say, for domestic products. And we sell a lot of what we would describe our lower end power meters for production line testing of white goods, for instance. And so, of course, that then becomes a price issue. Accuracy is not quite so important, because at this stage you've already proved the design, you're just doing a sampling or a test at the end of a production line. So high accuracy, you need to be able to know what the accuracy is, but it doesn't need to be so high as you would perhaps in a validation process of your design. What are the cons of a power analyzer? Well, limited or zero waveform analysis. So again, it's not so intuitive, because not on the power meters you don't see the waveform, it's just numbers. Generally, you can't measure intermittent power, because it's an averaging type power meter with a certain update rate. Although there is, on some of our models, the ability to do what we call a high-speed mode, which gives you some ability for data, but it's not the same. It doesn't give you the same control as you do on a waveform type product, for instance. I just wanted to, before I leave the subject of power meters and analyzers, talk about this one, which actually is our highest accuracy instrument. Just to give you a frame of reference, the WT300, which I've got sitting on the bench there, the sort of accuracy you're talking about there is what we would say is 0.1 plus 0.1. That means 0.1% of range, sorry, of reading plus 0.1% of range. So that is the sort of a ballpark figure of accuracy we provide on a power meter starting point. This one, which is the most accurate one available and stable, offers you around 5 times that. And of course you pay for that. But if you're looking for small changes in efficiency, let's say for instance for a PV inverter, and of course they're always trying to increase the efficiencies of these inverters. They're up around 98% now. But if you're looking for small changes in that efficiency, by its pure nature, in order to be able to guarantee you've got it, you've actually got to measure at the highest accuracy you possibly can. Because if you don't measure at high accuracy, you wouldn't know whether you're 0.1, 0.2% better or not. So it sort of forces you within the one instrument to be able to measure both input and output of your inverter. Thank you. In order to look for these small changes of efficiency. So that really forces you to go for the highest accuracy that you have available. Then we've added another instrument to the mix, which is a precision power scope. And basically, we try to bring the best of all worlds. We try to bring the accuracy capability of a power meter together with the intuitiveness and abilities of a waveform-based product. So in this way, we have built it like a power meter, so it's direct input of voltage and current, for instance, but with the analysis capabilities of an oscilloscope. So that means that we can do cycle by cycle and choose which part of your waveforms you measure the power. So if you've got varying power, for instance, if it's a process, I've mentioned a printer, for instance, or even a microwave, which basically has power on, power off periods, you can bring up your cursors and measure power of particular parts. And of course, this is something you can't do with a traditional averaging type power meter. And you can also do XY displays and do analysis of speed versus torque, for instance. And we can also do harmonics measurement because, of course, doing harmonics measurement is also a key requirement for some validation processes and standards as well. I'll throw in a few graphs here just to show you the sort of typical, not typical, but the specification of the power meter. And you can see we specify here the overall error, in this case, as a percentage of the range. This is at power factor 1. We also throw in the effect of very low power factors. Of course, at zero power factor, there's no power, so you can't. It's impossible to specify it as a percentage of reading. We have, by necessity, specified as a percentage of range, because otherwise, you're so close to zero, you'd have an infinite reading error because it's zero. And specifications, everything is specified. So the specifications for this instrument is 6 pages long, essentially, to be able to give you the ability to work out what the actual error is for your power measurement. How do you prove that? Well, that's by calibration. So as I mentioned, there is a difficulty in this subject. Worldwide, nobody can measure. There's only one laboratory that can calibrate at 200 kilohertz, and that's in Sweden. 4 other standard national laboratories that can calibrate at 100 kilohertz. And Yokogawa laboratory in Amersfoort in Holland is the 5th. We can also calibrate to 100 kilohertz. So if you need basically to calibrate at the frequency of the application you're using at, you basically need to go to a calibration laboratory which supports the frequency of measurement. A few examples of typical applications for the PX8000. So you can see there's quite a range of these. And just a reminder of my first slide talking about some questions you might need to ask yourself if you're talking about considering what sort of instrument is best to measure power. There is no best instrument. I'm afraid it does depend on what you need to measure and how you need to measure it. Sorry, I didn't give you the perfect answer. Anyway, thank you very much for your attention.